next to where you have your working for your T results and that kind of thing, once you get a nice clean sheet of paper, or steal off a friend or something like that, and we're going to solve this without T results, we're going to solve it with auxiliary angle. Okay? Do you remember me saying, I've said it a few times, auxiliary angle and T results, they're both ways of rephrasing an awkward question into a way that's better for us to solve. Okay? So sometimes you use T results because it's more convenient, sometimes you use auxiliary angle. After we go through this with the auxiliary angle, I'm going to let you decide which you prefer. Some people will always lean, some people are like, I just hate T results, whatever it is, right? Doesn't matter if it's good for T results, I don't like it. So you always go for auxiliary angle. Some people the reverse. I'll let you make the judgment. Okay? Now let's have a look at it. Let's think back to what we looked at with natural forms half an hour ago, okay? What natural form fits this best? Sine's out the front, so it's going to be a sine one. And there's a plus, so it should be x plus alpha. Okay? So, you start off by saying, remember, because both of these are, auxiliary angle and T results, they're both about rephrasing. That's why they both start off with let. Okay? So this time we're going to say, let this be equivalent to the natural form you just told me. Sine x plus alpha. Okay? Right, now given that, I can say R, I can go straight to this line, by the way. A few of you asked me before. Once you've established that this is talking about auxiliary angle, okay, you don't actually need to introduce the Pythagorean identity, really. You can just say that's 5 squared plus 12 squared. And the reason why I'm going straight to the positive value is because R is an amplitude, right? So don't forget to write that down. So that's a perfect square, which is kind of handy. Okay, so 13. So now, when I take my values for cos alpha and sine alpha, right, I can say cos alpha is equal to, now let's see here. When you do your expansion, which one's cos alpha going to go with? Because it's sine, they're flipped around. So this cos alpha should go with this sine x. Okay? So this is 5 on 13. If you're ever unsure about that, right, which one was which, just write out the full expansion. I'm trying to show you that you don't have to write out the full expansion if you're good at remembering it. But if you do a few questions and you're like, man, I'm consistently getting things wrong because I mix them up, that's a sign for you to write out the full thing. Question? You will not lose marks if you get the question right. If you get the question wrong, you will lose marks. And so, often, especially with like this one, because it's so common, right? Sorry, Captain Obvious says a day, right? Because it's so common, right? That's why I haven't bothered to write out the expansion. But the other ones, they don't come up nearly as frequently. So I'll write out the expansion just so I make sure I get the coefficients right. There's cos alpha. There's sine alpha. They're both positive. We chose it so that they would both be positive and I'll get an acute angle. Now, even though they're nice like numbers, okay, the number you're going to get out is not exact value. So what do you get for alpha? Let's just go 3 decimal places in radians. I think what I've got is 1.176, approximately. Okay, can someone just double check that on a calculator? Make sure. Yeah. Okay, great. All right, now I've got alpha, so I can say this question up here. Are you guys ready? Thank you. Is equal to 13 sine x plus this weirdo number here, okay, which is equal to 2. Right, now that I've done this, now that I've actually changed my equation here, this has a different domain to this, right? So it pays you to remember that this is actually 6.28, okay? Just file that number away in your head. You knew it already, okay? But just remember it as we keep on going through work, it becomes very important. All right, let's move that 13 over just so we can get this in the right shape to pop into the calculator. So that's 2 over 13. You take your sine inverse. Now, when you take sine inverse, right, it'll only tell you the first answer, right? But obviously we're looking for many, many answers, okay? So when you write down this first answer, I think I've got 0.154. You must remember, there are other ones here, okay? Now, you might expect 2 answers. In fact, if you remember this question, there are 2 answers. But I'm actually going to write down a few more. In this case, I'm going to write down 3. 4 is kind of safe, but it's sometimes excessive. I'm going to keep going, right? Now, sine is positive. Sine is positive, okay? So, in my quadrants here, I'm looking at this quadrant here, okay? So, the answer will just be whatever I get for theta. in this quadrant, it's also positive, right? So this would be 180 minus theta. Okay, in the second quadrant, that's what my answers look like. This is 180 plus theta, and this is 360. Sorry, I should have done it on pies. That's what you get for these two quadrants, but I'm not interested in them in this question because sine is positive, right? So I'm just going to ditch these two. Okay. So here's answer 1, theta, right? My next one will be pi minus that, right? Pi minus 0.154, okay? Now ordinarily we'd stop, but, and I wonder if you can see why I'm going to keep going, I'm going to do the next solution. Now, there's a solution in quadrant 1, solution in quadrant 2, can't do this one, can't do this one. You come around again, what's the next solution? It's this plus 2 pi, because that's the period of sine, right? So I'm going to go 2 pi plus 0.154. Okay. Now maybe you want to do a fourth one just to be safe, but it turns out to actually be okay in this case, right? So there's 6 solutions. Why did I note down 3? Let's actually just get their decimal values for all of them. We're going to work them out. I've got 154 here. 2.987, 6.438. Okay. Where do I go from here? Well, on the left-hand side, I don't have x on its own. So just like with t results, often you have x over 2 over here, so you multiply through by 2. Well, here, I have to add by my alpha, right? Or sorry, subtract in this case. Okay. So when you subtract 1.1676 off everything, okay, here's what we're going to get. Okay, so can you see why I pulled out a third solution? Okay, because this first solution, due to the sort of dark magic we did with auxiliary angle, is no longer a valid solution. Okay, it falls outside the domain once you've actually subtracted everything. Okay, and this one over here, 6.438, that's outside the normal domain, right? But we changed the domain, right? We moved it over. So actually when I subtract, it comes back within the domain that I was after, okay? So down here, just to finish, I would quote the domain. I would say, but I'm between 0 and 2 pi, okay? That's my reason for excluding this first answer here, okay? So x is equal to, and I hope those numbers look familiar from when we solved it the other day, okay? So this is what the auxiliary angle working looks like. You compare that, put it next to your T results working. I'm kind of not sure. Maybe because this is unfamiliar, you're like, yeah, I think I'll stick with T results. Or maybe you hate the quadratics you get with T results. Makes the working a bit longer, I think, if you compare it. But you need to be able to do both and choose which one you think is going to be the quickest. Yeah.
Are there some questions that auxiliary regulators T results back in the tab?
Yeah, so T results, I mentioned this, I think, just to you actually. T results, auxiliary angle only works in a specific case where you've got one wave function plus another. Okay, so a sine and a cosine, just one combination of those. Okay, if you add like a third wave function, like say cos 2x, okay, you don't get a big sine or a big cos curve. Okay, instead you get something with extra wiggles in it. You get weird things like that. So I can't approximate that with just a sine curve and change the amplitude and change the phase. In the same way, if you've got a tan in there, tan's not a wave function. It's got breaks in it and that kind of thing. So T results. So T results is a little more versatile. It can tackle a broader range of problems. But you get the x equals pi problem, and people get more confused with that domain than with this domain. Okay.